Hey everybody, it's Mr. Carr again. Today we're going to be talking about 10-3 day 2. Very similar to when we did our arithmetic sequences. We went into a little bit more deeper into it with the sums. That's what we're going to do today as well. We're going to look at the sums of n terms in a geometric series, as well as the sums of infinite geometric series. So that's going to be a little bit different of an idea. Okay, so let's first look at these two formulas. These are going to tell you the same exact thing. This is the sum of a finite, so it has a beginning and an end, a finite geometric series with n terms, or it's also called the nth partial sum of a geometric series, can be found using one of these two. You can use either one. It always just depends on what information you have. And so what's going to be easier to set up. So for example, you have a sub 1 here. Okay, if you have the first term, you notice that you need the first term no matter what. Okay, you need the number of terms here with the common ratio. Okay, and then you have the common ratio down below. So that's the three things you need for the first one. You need the first term, the common ratio, and the number of terms. Whereas when you look at the second one, you got the first term, you got the last term, and the common ratio. So if you know how many terms it is, or you know what the last term is, that helps you figure out which formula you're going to use. So let's take a look at this first example here. We want to find the sum of the first 11 terms of the geometric series 4, -6, 9, and so on. So if it says the first 11, we know that n is equal to 11. We have 11 terms here. Okay, we know that thanks to this, a sub 1 is just 4. So that means last thing I need is my common ratio. So my common ratio is going to be the ratio of consecutive terms. So I could take -6 divided by 4. I do that, I get a -1.5, or fraction -3/2. But for my formula that I'm going to use, it'll be easier to do the decimal version. So I want the sum of the first 11 terms, so it's going to look like this. The sum of the first 11, based on the information I have, I'm going to use the first version. So that's going to be a sub 1, which is 4, multiplied by 1 minus the common ratio, -1.5, raised to the 11th power, divided by 1 minus a -1.5. Okay? The biggest thing about using these formulas, you have to do this in your calculator properly. If it helps to simplify as much as you can, do that. But you also have to be careful about rounding. So personally, I'm going to go ahead and plug it all in my calculator at once. So I'm going to have 4 is multiplied by, we got, let's see here. My numerator is going to be 1 minus, and make sure you put the parentheses around your negative 1.5 here. So you got to make sure there's parentheses around that, because otherwise you'll get a little bit mixed up with your setup there. Okay. And then divided by 1 minus a -1.5. And that comes out to my sum, which is 139.996. Okay. So again, what this means is we continue this pattern on to go to 11 terms, and we add all those values up. The sum is going to be 139.996. Okay. Here's another one. Find the sum of the first n terms here. Given that the first term is -4, this a sub n is -65,536, and I got a common ratio of 2. So this is set up for the second equation. We have a sub 1, we have a sub n, and we have my common ratio. There is another way to do this. If you still want to just use the first formula, remember, we need the number of terms. So if you wanted to, you could set this up in a way so you can say that a sub n is equal to a sub 1 multiplied by r to the n minus 1. So if I plug in the information I have -65,536. I have my a sub 1 is -4. My common ratio is 2 raised to the n minus 1 power. So the goal here would be to solve this out to get for n. And once you have n, you can then use this formula if you wanted to. This is a method for doing this where you don't have to use the second formula at all. You just have to remember the first formula. So again, doing this, you're going to turn this into an exponential. You use the 1-1 property to solve for the n at that point, or we just go right to that second formula. So the second formula is the sum of the n number of terms is going to be a sub 1, which is -4, minus a sub n, which is -65,536, multiplied by the common ratio 2, all divided by 1 minus 2. Okay, so the sum of these n terms, we go ahead and do that in the calculator, Again, be careful with your negative signs and parentheses, but -4 minus a -65,536 times 2 divided by 1 minus 2. So I get that in, I get -131,068 for my sum. All right. So the next one we can use is our sigma notation. Now, I'll do this one real quick with the calculator. You have the ability to do the sigma notation in your calculator. You do not have to do with our sum formula now, but I'm going to show you both. So the thing to recognize, well, let's start with just putting this in. You can just plug this in exactly as it is, go into Desmos, your graphing calculator. So n equals 3, you're going from the third term to the eighth term. It's going to follow this rule. So this is what I'm going to do that one. So I'm going to pull up the sum here. We're going to go from the third term up to the eighth term. Put some parentheses here. So I'm going to plug inside. That was a -2. That is multiplied by a -2 being raised to the n minus 1. And that's going to have to get its own set of parentheses in the exponent there. So n minus 1. Okay. So this is exactly what is in the example. The answer is 168. So using your calculator, go for it. Okay, unless it says to apply a certain formula, we're going to just go ahead and leave that right there as 168. But I want to show how this does compare to our other formulas that we just learned. This is a geometric sequence because -2 is raised to the n minus 1. That's my common ratio. This is r is -2. Remember, if I look at the formula, I definitely need to know a sub 1. So in this scenario, I can kind of treat my third term here as my a sub 1. It's where I'm starting at in my sequence. Okay, so in this case, I'm going to do this. I'm going to do -2 times -2 raised to the 3 minus 1 power. So it's a sub 1, but it's really a sub 3. I'm just calling it a sub 1 because that's where I'm starting in my formula for the sum formula. Okay, so that's going to be -2 times, this will be -2 to the second power, which is a +4. So a sub 1 is equal to 8. So I'm going to start my sequence at 8, and I want to go to the eighth term here. So remember with that, the number of terms it takes to get from 3 to 8, that's going to be 8 minus 3, but then I have to add 1 on that one to count for that starting spot. So that gives me 6. So I now have a sub 1, I have n, and I have my common ratio. So I can use this version here. It's a sub 1 times 1 minus r to the n divided by 1 minus r. So I have everything for this formula. So that's going to be the sum of these 6 terms is going to be a sub 1, which was, oh, I'm sorry, that was a -8 for that one. -8 times 1 minus -2 to the 6th power over 1 minus a -2. Okay, so I've got, excuse me. So 1 minus in there. Just plugging this all in my calculator as is. So I've got 2 to the 6th and -8. So when I plug that in my calculator, I get the sum of the 6 terms as 168. So again, just making that connection between the sigma notation and my sum formula. We're telling the same thing in there. So your calculator is basically doing that formula all on its own. Okay. The other thing we're going to talk about is the sum of an infinite. So everything we've covered so far is a finite geometric series. For an infinite series, this is one that can go on forever. We have a special formula as long as your common ratio, or the absolute value of your common ratio, is less than 1. What happens with a common ratio of less than 1, think about it like this. If your common ratio is 1/2, you multiply something by 1/2, it gets smaller, times 1/2 is smaller, times 1/2 is smaller. These numbers are getting smaller and smaller and smaller and getting close to the value of 0. This is what's called a convergent series. So if you have a convergent series where r is a value that is less than 1, and I should say the absolute value of that, then you can figure out what the sum of the entire series is from this formula. It's a sub 1 divided by 1 minus r. Now, again, this only works for a convergence series, because if it's divergent, meaning that it's growing, so if my common ratio is 2, my terms are growing and growing, this doesn't work that way. There is no limit to that, to the sum. Whereas this one, it will go to a certain value. Because the idea is that if I keep going, like, for example, 1/2, all my terms are getting really close to 0. So I'm not adding anything else that's significantly more. So eventually you're just going to be adding these really small decimal numbers. So it's basically just the number that you're approaching on that one. So let's take a look at that example right here. So if possible, find the sum of the infinite geometric series like this. So again, all we need are two pieces of information. We got a sub 1 and r. We have a sub 1 is 24. R I'm going to get from taking 18 divided by 24, which is the same as, let's see, divided by 6 is 3/4, or 0.75. All right. Since this ratio is less than 1, I can go ahead and plug this in the formula. So that's going to be a sub 1, which is 24, divided by 1 minus 0.75. Okay, so that is going to be 24 divided by 0.25, which is going to come out as 96. Okay, this is the sum of all the possible numbers, because again, if I keep going on and on and on, these values, because they keep getting smaller and smaller and smaller, I'm eventually going to be adding something that's really small and like really close to 0. So if I'm adding something that's really close to 0, I'm not changing the value at all. Okay. We look at this next example. If possible, find the sum of this infinite geometric series. So here's my a sub 1. For my r, I want to take 0.66 divided by 0.33. So I just take that ratio of the consecutive terms. That comes out as 2. So since this number is greater than 1, so since r is greater than 1, I should say the absolute value of r is greater than 1, then the series is divergent, and I cannot find the sum. Okay, so this sum is not possible because it's a divergent, and that's because r is greater than 1. All right, one more example we can look at, and that's going to be a real life problem like this. This one's going to be got a little bit of extra challenge to it because it's got some extra stuff going on here. So we have a ball that's being dropped from a height of 20 meters and bounces 4/5 of the distance after each bounce. How far does the ball travel upward after it hits the ground the third time? So I want to model this scenario. So the first thing I want to do is I want to figure out what's my a sub 1. I'm going to call a sub 1 the height after its first bounce. So this is going to be 20 times 4/5. Okay, so it starts at 20, but after it bounces one time, it's going to go up 4/5 the height of that. So multiply that out, and that comes out to 16. So a sub 1 is going to be 16. My common ratio here is the 4/5. So that means I can do my explicit rule to help me find the third time. Now, granted, I could just do this times 4/5 again and times 4/5 one more time to get the third bounce. But I want to practice using my explicit rule. So a sub 3 is going to equal to a sub 116 multiplied by 4/5 raised to the 3 minus 1 power. So the third bounce here is going to be equal to 16 times 4/5 raised to the second power. So go ahead and plug that in. So I got 16 times 4/5 raised to the second power. And I'm going to get 10.24. And this is going to be meters for that one. So after the third bounce, it reaches a height of 10.24 meters. Was the total vertical distance going up and down the ball travels before coming to a rest? So think about what's happening with this ball. It drops from about 20, bounces up, and it comes down, bounces up, and it's coming down. Eventually, the bouncing is going to go really low and be 0, basically. Okay? So that's what we're trying to figure out. Now, with my terminology here, if I call that my first term, that's technically starting it right here. That is the distance it travels to go up. So the next number, this is a sub 2, is how far does it go up, and how far does it go up here and up here. So I can treat that as my sum of my infinite series. What is going to be that total distance it travels up every time? So I'm going to start with that as my definition. I've got everything I need here. So the sum of taking a sub 1, which is 16, divided by 1 minus I could do 1 minus 0.8 because that's the same as 4/5. Okay. So if I find this sum, I'm going to take 16 divided by 0.2, and that comes out to 80. 80 is representing how many meters it's traveling up in all of the sequences. So what that means then too is if that's 80 for everything going up, it also has all these values coming down. So I'm going to double that. So I'm going to take 80 times 2 to get 160 meters. So this is all of the bounces going up and down, up and down. But there's still one more thing. Because I started here at 20 meters high, that initial dropping, that 20 meters to go down, I want to add that down here. So the actual actual geometric sequence was the bouncing up and down, up and down. The first drop, I'm just going to go ahead and add the 20 to that. So what I get is a total of 800 meters that this ball travels down and up. Okay. So again, we took our infinite series, we doubled that because we have to consider going both up and down. And then because this is only modeling going up in the bounces. And then we still add that 20 from that initial drop. And that's it for today. So we looked at our infinite series. We looked at our finite sums as well. Again, we have our specific formulas that handle both the infinite and finite series. It's all a matter of having the proper information. So that's it for today. Take care, everyone.